And today we're having Ajeeth, and he's going to talk about honeycombs and factorial dual Grothendieck polynomials. Thank you, everyone, for coming.
Thank you. Thank you for having me. Can you hear me?
Yes.
Yeah.
So I'm going to try to tell you the story that I've been through over the past couple of years since I started my PhD with my advisor, Paul Zinn-Justin. And this work is based on my work with Paul and Travis Scrimshaw. Yeah. So let me start with some motivation from geometry. If you don't know any geometry, please don't worry about it. All you need to know is that there is a ring and there is a basis. And we are trying to compute the product of the basis elements. So let's start with the Grassmannian. Grassmannian is a k-dimensional subspaces of an n-dimensional space. I want to consider the product of two Grassmannians. I'm going to define this map ds, short for direct sum. I'm going to map them into a bigger Grassmannian. So it's v cross w goes to v direct sum w. But this map induces a pullback on k theory of Grassmannian. And there's an interesting basis for this ring. And what we want to do is we want to take image of one of those basis elements. The only thing you should know about Schubert basis is that they are indexed by partitions. That's the only thing I will be using. So I want to take the image of Schubert element and I want to expand it in the basis. What we want to compute is the constants that appear in this expansion. I'm going to call this co-product structure constants. And this map is GL1, GLN cross GLN2 equivariant. So you can do the same thing for equivariant K theory. I'll just denote T for equivariance. And you ask the same question: what are the structure constants? Whenever you're in this situation, there are two questions you can ask. One is there a combinatorial formula for these co-product constants? And the second question is, are there a set of polynomials whose product structure constants are these constants? Now, of course, my interest is to use the techniques from integrable systems to compute these constants. And this technique was introduced by Zinn-Justin in 2009. What you do is you start with a set of polynomials and the lattice model for them. Actually, let me show you this. Let me show you this technique through this example of Grothendieck polynomials. Grothendieck polynomials are symmetric polynomials, and they're the polynomial representatives of Schubert classes in this K theory of Grassmannian. And the factorial Grothendieck polynomials introduced by Peter McNamara, they are the polynomial representatives of Schubert varieties, Schubert classes in the K equivariant ring of Grassmannian. So the first part of the technique is to have a lattice model for these polynomials. So this is a lattice model. And if you consider the partition function of this grid with these Boltzmann weights, you get the Grothendieck polynomial. How do you get a factorial Grothendieck polynomial? It's pretty simple in the realm of integrable systems. You just attach variables to the physical, you attach variables to the vertical lines, and I'll call these as physical variables. Okay, then you take this lattice model and you embed them in a higher rank model. And it satisfies a Yang-Baxter equation. And you compute a partition function of a bigger, of this shape. And you do the Yang-Baxter equation and you get the structure constants. I know I'm being a bit vague here, but there are only two things that I want to emphasize here. The first thing is that to be able to do this technique, you should know a conjecture. You should know what kind of combinatorial object are you searching for. So in this case, we were using, they were using puzzles. And I'll show you what a puzzle is in a bit. So first, you need to have a conjecture or a proof or a theorem that will tell you what kind of combinatorial objects are you looking for. And secondly, the equivariance kind of comes for free in the case of integrable systems. You just attach, like I showed you here, you just attach physical variables and you get the equivariant structure functions. So this is what we're going to do for dual Grothendieck polynomials. We're going to come up with a lattice model and we're going to embed them in a higher rank models. We'll do this Yang-Baxter. We'll apply this Yang-Baxter equation to get the structure constant, right? And this is, yeah. So let me just give you some formulas for D nu lambda mu. So the first formula was given by Anders Book in his 2002 paper in terms of set value tableau. I'm not going to talk about that, but I'll talk about this recent formula given by Pilavsky and Yang. So whenever you have a partition, you can associate a 0-1 string to it. Basically, for every vertical line you attach 1, and for every horizontal line, you record a 0. So whenever a partition is considered contained in a rectangle, you will get this 0-1 string. And puzzles were introduced by Knudsen, Tao, and Woodward, and they compute the structure constants for Schur polynomials. So what is a puzzle? Puzzle is this equilateral triangle. It's a tiling of this equilateral triangle with 3 little pieces. And the boundary is encoded as lambda. And nu. Then the number of ways to fill this triangle with this boundary is equal to, with these little pieces, is equal to this coefficient, which are the Littlewood-Richardson coefficients. And what Wokin said was, if you introduce this extra 10-10-10 piece, and in only in this orientation, you get the structure constants for Grothendieck polynomials. And what Pilavsky and Yang said, if you introduce this hexagonal piece, and every such piece gets a weight of -1, and if you introduce this piece, they will compute you the d lambda. So here's an example. So this coefficient is -2, and you have, these are the corresponding 2 pictures of it. And every time, like I said, every time you have an hexagonal piece, it picks up the weight of -1. So -1 plus -1 -2. But this is not ideal in the realm of integrable systems, because if you're going to study the underlying lattice model integrability of this puzzle pieces, you can't break this hexagonal piece into. You cannot realize this hexagonal piece as an entry of an R matrix, basically. So we need a different combinatorial model which is local and which is in the realm of integrable systems. I should stop saying the realm. Okay, so to get there, we started thinking about honeycombs. Now, in this case, we'll encode partition by column multiplicities. So here you have 2 columns of size 0. You have 1 column of size 1 and 0 columns of size 2, 1 column of size 3 and 3 columns of size 4. That's how we're going to encode our partitions. Now, again, honeycombs were introduced by Knudsen, Tao, and Woodward in their study of the saturation conjecture. What is a honeycomb? Honeycomb is a picture like this, where 3 semi-infinite lines come from 3 directions. And they all meet and satisfy a certain balanced condition. And you encode lambda, just like puzzles, lambda, mu, and nu. So, yeah. So we wanted to generalize these honeycombs. The way we generalize is that we're gonna let the lines turn a little bit before they meet. So I'm gonna call these things as vortex. And every vortex picks a charge of -1. And these are the corresponding 2 pictures of generalized honeycombs that are, yeah, this coefficient was -2. No, this is really local in the sense that we can represent these little pieces as an entry of R matrices. And there's a really interesting fact about these polynomials, sorry, these modified honeycombs. There's only there's only a couple of choices for you to introduce vortices. One is this kind of a vortex, and the other one is you let them turn the other way. And the product, you can allow more lines, but the problem with that will be the product that this will define won't be associative anymore. Yeah. So these compute the structure constants for these constants. And I'm not going to tell you what these objects compute. Maybe at the end of the talk I'll tell you. It's just going to confuse us. Any questions, please? Okay, so now we want to use polynomials, right? So what are the polynomials that we need to consider to compute those D coproduct structure constants? These are called dual Grothendieck polynomials. And dual Grothendieck polynomials were introduced by Thomas Lamb and Piliavsky. They are a generating series over reverse plane partitions. The reverse plane partition is the filling of the Young diagram where the entries are weakly increasing along both columns and rows. And the way you assign a weight to such filling is that if you look at the entry I, you look at the number of different columns that contain it. So here in this case, I have two columns that contain 1, so it's x1 squared. One column that contains 1 and one column that contains 2, so it's x1 times x2. And here we have two columns that contain 2, so it's x2 squared, and so on. Now from this definition, you can right away see that G lambda dual Grothendieck polynomial is of the form that S lambda plus lower order terms, where S lambda is a sure polynomial. And these polynomials are dual to Grothendieck polynomials under the Hall-Emmett product. And they form a basis for the ring of symmetric polynomials. So you start with take the product of two of such polynomials and you expand them in there. And the constants that appear are the coproduct structure constants that we wanted to compute. This is all non-equivariance. There is no formula for structure constants in the case of the equivariant coproduct structure constants. Not in terms of Tableau, puzzles, honeycombs. No, we don't know anything. Yeah. Okay, so now we wanted, so since we had a conjecture in terms of honeycombs, this prompted us to study some bosonic lattice models for these dual Grothendieck polynomials. Yeah, so consider this R matrix. Your A, B, C, Ds can be any positive integers. And these are the weights. The only condition is that they satisfy the conservation. So A plus B is equals to C plus D. And this R matrix satisfies the Young-Baxter equation and the unitarity relations. And if you just use this R matrix and encode your partitions, the column multiplicities, and if you consider the partition function of this grid, you will get Grothendieck polynomials. Now, if you like pipe dreams, you can think of this model as bosonic pipe dreams, because if you look at this vertex, this is always 0. And since the boundary condition at the bottom is 0, this has to be 0. And so on. So the only non-trivial contribution comes from the upper half of the antidiagonal. And when I'll use the star to denote that the boundary is free. Just there are no restrictions on the left boundary. Okay, so what is the lattice model for dual Grothendieck polynomials? Okay, we need a different L matrix. Now it's the same. A, B, C, Ds are again can be any positive integers, and the only condition is that A plus B is equals to C plus D. And the way we assign the weight x to the power of minimum of A and D. And here again, we are encoding our partitions through column multiplicity. And if you consider the partition function of this grid with this L matrix, you will get G lambda. you get the dual Grothendieck. Okay, so I don't know if this L matrix satisfies the M-Baxter equation, but we don't need it. What I know is that this L matrix satisfies the RLL relations with the R matrix that I showed, which means you can move it across. Right. Another important thing that I want to mention is the R matrix here, it satisfies the difference property. By difference property, I mean the R matrix is independent of scaling of the variables. So if I translate x to, send x to x over z and y to y over z, the R matrix is independent of z. That's what I'm going to call as a difference property. So it satisfies the difference, which means now we can introduce these physical variables to it. So let me define this new L matrix as x of x comma z as the same conditions where a, b, c, d can be any positive integer. And my Boltzmann weight now is x over z to the power of minimum of a comma t. And you can show that these polynomials are symmetric because the R matrix is independent, and so you can move it across. But unfortunately, this doesn't solve the problem that we wanted to solve. Okay, everything is nice. Okay, we have a conjecture for the structure constants. We have the R matrix that satisfies the difference property, but these polynomials are not dual to factorial Grothendieck. Yeah, so we wanted polynomials that are dual to factorial Grothendieck. So we needed a different model. And Travis, when we met Travis showed us a different model for this dual Grothendieck polynomial. And now my horizontal lines can carry any positive integers, but my vertical lines can only carry fermionic labels, which is 0 and 1. So this is our L matrix. And this is the R matrix with which this L matrix satisfies the RLL relation. And if you consider the partition function of this grid, now here we are encoding lambda with fermionic and as a 0-1 string. But this is disappointing at the first look because the R matrix doesn't satisfy the difference property, which means we don't know we can't introduce this physical variables just like we did in the previous case. So what do we do? I agree that difference property is not a necessary requirement, to be able to introduce physical variables. But the question is, how do you introduce them? I don't have a guiding principle, but somehow we were able to introduce the physical variables in this way. This is totally non-trivial. Yeah, and we realized that if you introduce Boltzmann weights in this fashion, and then the R matrix will be again independent of the physical variables. So you can, move the R matrix across all the vertical lines. And this will give you what we call factorial dual Grothendieck polynomial. And these polynomials are dual to factorial Grothendieck. And they satisfy this nice Cauchy identity. Any questions? So now we have factorial dual Grothendieck polynomials, but we don't have a conjecture for the structure, for instance. So we are kind of stuck in this solving this. We're kind of stuck in solving this problem. So now I'm going to move to it. I'm going to give you more lattice model. So this is the end of my first part of the talk, and in the second part, I'm going to talk about a different set of polynomials. So G lambda are symmetric polynomials. And there's a standard involution map that sends sure function S lambda to its S lambda prime. Then you can ask, what are these polynomials? What is the image of dual Grothendieck polynomial under this involution map? And these polynomials are called, I'm going to denote them by J lambda, and these are called weak dual Grothendieck polynomials. And they have the same structure constants as G lambda. Now let me give you the Boltzmann weights for. Yeah, okay, so let me denote this L matrix by small l. Here my vertical line is bosonic, but my vertical line is bosonic, and my auxiliary line is fermionic. 0, 0, and 1. Okay, so we need an R matrix that intertwines this L matrix, and it is of following form. Okay, why am I talking about these? Right, I wanted to show you an interesting relation between. Yeah, okay. So let's build a transfer matrix for these polynomials. Transfer matrix is just one row by concatenating lots of vertices, and the right boundary will be 0, and the left boundary is free. Yeah, and how do you get this polynomial? This polynomial is nothing but 0. And what kind of encoding am I using here? I'm using column column multiplicity. Okay, so let me denote the transfer matrix for the dual Grothendieck polynomials from previous model as T tilde. Just to recall, the L matrix was had A, B, C, D, then so the Boltzmann weight was x to the power of minimum of A, comma D. And let me denote, yeah, again, you define the matrix in the similar way. And this is free boundary. And G lambda x1. There is no reason for us to expect any relation between these two transfer matrices. But what they do satisfy this interesting relation, which we call inversion relation. Which is T of x times T of minus T tilde of minus is equals to the identity.
Can you just remind me that J lambda is the omega of G lambda? Is that correct?
Yeah.
Okay, thank you.
Thank you. Now let's do a similar thing for Grothendieck polynomials. Yusuf's have observed that, sorry if I spelled your name wrong. Sorry if I misspelled your name. Okay, so what he said was, okay, you can ask the same question for Grothendieck polynomials. What are Grothendieck polynomials? What are the image of Grothendieck polynomials under this convolution? What he said was, start with Grothendieck polynomials and do a slight change of variables, which is 1 minus 1 plus beta x, 1 minus alpha x. And if you do this polynomial, do this transformation, after this transformation, let me denote those polynomials by g of alpha comma beta of x. Okay, again, these are again symmetric polynomials, and the products and coproduct structure functions are the same. And if you apply the involution map to this polynomials, g lambda, you get g lambda prime with beta and alpha swap. So I'm going to drop alpha and beta, but I'm just going to consider Grothendieck polynomials. So so let me just consider the involution of Grothendieck, which is alpha is 0 and beta is minus 1. And you get g of minus 1 comma 0 lambda. Now, what are these polynomials? These polynomials are usually denoted by j lambda. These are called weak symmetric Grothendieck polynomials. And the lattice model for them is the following. Yeah, I think this is right. Maybe up to some sign. I don't know. And here again, it's the same same thing that we've been doing. So the boundary, the bottom is 0, the right is zeros, and the top you encode by column multiplicities, and your left boundary is free. And this is your weak Grothendieck polynomial. Now let me denote this transform matrix as just T of X, which is built from these vertices. And this will be the free boundary. And the similar inversion relation holds for these transform matrices and the transform matrices from the Grothendieck model that I showed you before. Just to recall the Boltzmann weight. And let me denote the transform matrix built from these vertices as T tilde of X. And what we and a similar inversion relation holds for these polynomials, which is T of X times T of minus T tilde of X over 1 minus X. Okay, so what are the Cauchy identities? So you can prove Cauchy identities. You can prove the following Cauchy identities. So if you take G lambda, of course they are dual, so they have to satisfy this Cauchy identity. And for the weak dual Grothendieck, they satisfy the Cauchy identity with the weak Grothendieck polynomials. Okay, how do we prove this? Let me just show you how to prove the prove this thing. So let's say you have, so you prove a RLL relation, right? So it goes something like this. Now, if you apply this inversion relation from yeah, just multiply it with T tilde of minus X. We're going to multiply with T tilde of X. Sorry. So we can take T of minus X because we want to apply the inversion relation times T of Y is equals to 1 plus X times T of Y times T of X, T of minus X. Now we'll multiply with T tilde of X. So this will give you on both sides. This will give you T of Y times T tilde of X times 1 plus XY is equals to T tilde of X times T of Y. So what this means is if you by applying this relation, you can derive a different identity involving these two polynomials. For example, the first identity can be, so if you apply, after doing this, you'll get that j lambda prime of x times g lambda of y satisfies the dual Cauchy identity. And similarly, you can do the other way, which is g lambda of x times j lambda prime of y equals to 1 plus xi yj. Yeah, sorry for the short talk, but that is all I have to say. Thank you.
Okay, that's great. Thank the speaker. Okay.